Okay, one more thing, and then I really want to clean up how it is that in this experiment that static friction doesn't screw us up. But I need the rotational version of the work energy theorem. And so very quickly, it's just the same thing that we did before when we considered what's changing kinetic energy. This time, for your convenience or otherwise, I didn't take the time derivative. I took the total differential. Here's the kinetic energy in the form that we derived right there for a rotating body. And if I take the differential, the only variable is theta dot, so a little bit of a change in the kinetic energy can come about because we changed the angular velocity, theta dot. The 2 went away because that's the way derivatives work. Now I am going to say that d theta dot is equal to d theta dot dt multiplied by dt, and shuffle d theta dot dt, which is theta double dot, to the front, exchanging the order of angular velocity and angular acceleration so that I can look at the moment of inertia times the angular acceleration and say that's the net torque on the object. So torque, that's getting back to what Kevin was talking about. So the torque is equal to, or causes, the time rate of change of the angular momentum. And theta dot dt, I'm converting back into just a change in the rotation. Yes, sir?
Just to be clear, in the first line and the second line, we're
Yep.
taking dk d theta dot and then multiplying both sides by d theta dot. Is that what happened there?
No. So if I have k is equal to 1/2 I omega squared, dk would be equal to 1/2 I 2 omega d omega. Right?
Sure, yeah, I got the 2 cancel there.
And this is my theta dot d theta dot.
Right. Maybe I'm just thinking of the differentiation, but I think I see where that comes from.
Okay? Yep. How many of you have done integration by parts? Okay, doesn't this look familiar from integration by parts? I'll take that as a resounding sense of fulfillment and rejoicing.
And there was much rejoicing.
And there was a whole boatload of rejoicing. Okay, so this term here, the torque turned through an infinitesimal angle, tau net d theta, is a little bit of rotational work. Just like before, if we moved a force through a displacement, we did a bit of work. So this is the rotational analog of the work energy theorem. Before, we had dk was equal to F net dot dr. And now we have change in kinetic energy is the net torque times the change in the rotational position. So those are just analogous. So I want to explain why friction doesn't screw up energy conservation as the things roll down. So if I just consider this disk of mass m and radius r, and it rolls down the incline, these are the forces, I think, on the disk. So we have gravity at the center of mass. We have a normal force that's applied at the point of contact and normal to the incline. and we have a force of static friction. Now, is it clear that that needs to point up the incline, not down? Okay? Think about now from the point of view of being at the center of the disk, which way is that going to make the disk rotate? Clockwise or counterclockwise? Clockwise. That's going to make it spin around this way. Okay? So if the center translates by a distance d, let's calculate the total work that's done by the force of static friction. So the translational part of the work is just what we wrote here. That's going to be the force of static friction dotted into the displacement integrated over the whole displacement. But the force of friction is opposite to the direction of displacement, so we get a negative. So what's happening is that static friction is taking energy away from the translational motion, because that's negative. So it's doing negative work. But now let's consider the rotational work. So the work done by static friction on rotation, according to the expression here, is the torque multiplying the change in angle. So the torque of static friction about the center of mass is F sub, that's nice. F sub s is perpendicular to the radius, right? So it's just F sub s times the radius multiplied by a little change in the angle, and that should have been not a phi, but a, that should be a phi. Okay, as it rolls down, how much will the angle change? Well, it would be d divided by the radius. So the radius drops out, and we just get the force of static friction multiplied against d, which is exactly the same as this term. So we add them up, and we get no change. So static friction is just slowing down the translation, so it throws some of the energy into rotation. Exactly. And there was much rejoicing. All right, any questions about that? That's it until the, yes?
Does that calculation hold for kinetic friction as well?
No. So if it's sliding, then where is the energy going to go in part? It will go towards heating the surfaces. But notice that I made the point a few times that the point of contact is not sliding. There's no motion of the force at the point of contact, so it does no net work. So tomorrow,
Midterm 2.
well, there's midterm 2 in red, but then movies, 1 o'clock and 3 o'clock.
You're trying to distract us from going out what?